Hello. Hi guys, good morning. Welcome back to a new video. Ki hal chal? I hope you guys are doing good. In this week on the problem, reverse odd levels of binary tree. Make sure to read the problem very carefully. It simply says we are given the root of a perfect binary tree. Again, what if you don't know what the perfect binary tree is? Perfect binary tree is every node have exactly two children. So this node have exactly two children, and also you might say, Aryan, okay, is this also perfect binary because every node has exactly two children? No, technically you might say, okay, the leaf nodes will always have no children, but it also says that all the leaf nodes should be at the same level. So in total you can imagine that a perfect binary tree will have all nodes as two child nodes or zero child nodes, but the ones having zero child nodes will be actually the leaf nodes, and all the leaf nodes will be at the same level. This is a perfect binary tree. Now you have to reverse the nodes values at each odd level. What is the meaning of odd level? This is level 0, this is level 1, this is level 2, this is level 3. 0, 1, 2, 3. So at odd level, just simply reverse these node values. Make sure there's a stress on it. You have to not reverse the nodes, you have to reverse the node values. And again, that is ultimately why this problem is easy. Again, not medium but easy. So they are given what the reverse means. Reverse simply means if you have the value, if I take this specific level and the value is 2, 1, 3, 4, 7, 11, 20 and 18, I'll simply reverse it. I'll get this value. Simply return the new root node, or I should say the root node with the reverse tree. And they are given that what a binary tree and all the stuff, what is the level. So ultimately, if you just look at this example, it is level 0, level 1, level 2, odd level is this one. So you have to simply take this level out and reverse it. As you can see, after reversing it, it became a 5, 3. And ultimately simply keep on traversing down. And as you know that it is simply a value reversal. So I just have to pick up this value out. Again, I don't have to restructure the tree. No, the child, this node and its corresponding child will not be restructured. And this is what this problem is, why this problem is easy, because I don't have to restructure this child and just have to worry about this child. No, I just have to remove this value. Now just get this value somewhere out, let's say 3, 5, and then simply put it back by reversing it. So after reversing, it will become a 5, 3. Just put it back 5 and then 3. That's your answer. Now as you simply can see that what I'm doing, my maksad, my main aim is to go on to every odd level and simply get the corresponding values, reverse it and paste it back. So ultimately I am concerned about level, and this is a simple tree. So I have a simple tree, I have to traverse level wise, simply which what comes to our mind is BFS traversal. So I'll simply, again, that's the most intuitive stuff. I can simply use a BFS traversal. I will iterate on this specific tree level wise on my odd level, where the level mod 2 is actually 1. I will simply grab out all the nodes, and after I grab out all these nodes, I will simply just get, again, I can get it to another vector or something, and then I can simply make sure to swap these values, as in to, again, just to reverse anything. Let's say if I have some specific vector, I have to reverse something. What usually we do? We simply, let's say if I have three, let's say let's take this one. 1, 2, 3, 4, 5, 6, 7, 8. Now to reverse it, there are multiple ways. First way is to take another vector and then put all these values into another vector, or another most optimized space efficient way is just simply swap these two values, swap these two values, swap these two values, swap these two values. It will simply be reversed. How? Let's see. So I'll swap these two, it will become 8, 1. Swap these two, it will become 7, 2. So you see that I'm reversing it from the, like, as in, like, if you iterate from left to right, it is being reversed as right to left. Same way, it will become a 6, 3. It will become a 5, 4. And now you can see it is reversed in place without using extra vector. And that's what the most obvious thing what we can do here. And again, like if you want me to do a simple dry run, that's also we can do. But the idea you understood, right? That we just simply go to all the levels. We can just simply get it into one vector and then we can simply swap it. So the same iteration we have here, that I have a corresponding queue. I'll push the root node in my queue. Current level for the root node is 0. Then I will iterate on the entire, like until my queue becomes empty. As you can see, this is simply a BFS traversal. Simply a very simple BFS traversal. Then I will check the corresponding queue size, because again, in a BFS traversal you have to go per level basis. So I'll go on a per level basis. Okay, for this level itself, just empty out the entire level. When I say empty out, make sure to push all the node values. Again, this is a node value. This is like entire node itself. Why I'm not putting the node value? Because I will swap values in the next step. So I will push out all the nodes in the current level inside a vector. So as you can see, I'll push the current node inside a vector, and then I will again know, that I have to simply call and do my push if I don't have that empty child. So I'll simply push it inside my queue, the corresponding children. So this part will make sure that for any node, I will, let's say my queue right now has the elements 3, 5. I am emptying out by iterating on the corresponding queue. As you can see, let's say if I have like all these nodes 3, 5, I'm just emptying out this corresponding queue, and in my updated queue, which is right now in this state, I will simply remove my 3. Again, I know that I have to remove up to this specific size. I'll simply remove it, and then I will simply push 8 and 30. Then I'll remove 5. I'll push 21 and 34. This is my queue state, new queue state. But I've also parallelly made sure that this queue elements, while I was iterating onto them, I'm also putting the corresponding nodes inside a vector. I will see that when they will be useful. But this portion is pushing the corresponding children in the queue itself, and this portion is just pushing up to a new vector. Now this new vector, as I told previously, will help me to reverse for odd levels. So if the level is odd, and as I told you, there are two ways to reverse it. Either you take another array, which will take extra space, or you can just reverse at the same place by simply using a two pointer. As you can see, why I say two pointer? Because if I have 1, 2, 3, 4, 5, 6, 7, 8, I can simply have L here and R here, and this is what I was doing. I was swapping these two. Then I will move both of them forward. I will swap these two. So this is simply a two pointer technique, right? So what I will do, I will simply have my left and my right at start and end of my current vector, and I will until I reach the midpoint, I will simply swap. But here make sure you're only concerned about the values. So I'll simply make sure I will swap only and only their values. So if I have this node 3, node 5, because I have pushed in my vector, I have pushed the node, so I can now swap this node with this 5. So just imagine that you have a L here and you have a R here, and then you're just swapping the node values. It is becoming 8, it is becoming 1. This is what you are doing. And with this, you are swapping, and also you know that you have already pushed their children in the queue itself. Ultimately, this is your maqsad, which is done. Simply move to the, or I should say increase the current level by 1, because you are about to go to the next level. And this is the corresponding answer, right? Give the corresponding root. Now, because you're iterating on all the elements, your time is O of n, because it is a perfect binary tree. Now, in a perfect binary tree, if I have n nodes inside my binary tree, obviously how the configuration will look like is 1, 2, 4, 8, and so on and so forth. Up till last will be n by 2. So again, if you want to just visualize it, just think of it as, okay, if you have a tree given here, you had in total 1, 2, 3, 4, 5, 6, 7, 7 nodes, right? First level 1 node, second level 2 node, third level 4 nodes, and next level will have 8 nodes, and so on and so forth. So how it looks like, okay, it is 1 plus 2 plus 4 up till so on and so forth, and the value is n. Now again, it's a simple technique which I'm not sure like if you guys know or not, but you will simply, again, just even not to go mathematical, you will simply realize that this last level will actually be nothing but n by 2, or I should say Again, don't take floor or seal. Again, just get the idea that you can see n by 2. Obviously, it is a seal value. But the idea here is that the last level will have equal number of nodes, which is the summation of all the other levels in the tree. That's a simple observation of a perfect binary tree. So last level will have, and as you can see also by mathematical terms, n by 2, which means the other nodes will also be n by 2, which means all the other nodes above this last level will actually be n by 2. And considering my queue stores all the nodes for one level at a time, thus in worst case I could have last level all the nodes inside my queue, which makes my time complexity, space to be O of n by 2, which is nothing but O of n, and that's my space is O of n. Now, although it's the most intuitive, but let's say the interviewer asks you to optimize it, can you do it? Now obviously the time will be O of n, that cannot change because you have to iterate on all the elements no matter what. Space right now is O of n. Now, obviously, I am doing simply a traversal, and that's what ultimately I'm required to do. But I'm using a O of n space. Now, the interviewer is asking me to optimize it. Now, the only optimization from at this point can be either O of log n or O of 1. Now, considering again, O of 1 to achieve is actually very far-fetched thing, and maybe like to overthink. Maybe I'm just trying to think here. What if I want to go ahead with O of log n approach? Then what can I use? Simply, if you remember that if we do a simple DFS traversal, then because it is a recursive depth of my entire tree traversal, then it can take O of log n time. Now, you might argue with me, Aryan, what about if the tree is skewed? Yeah, obviously, in that case, the space used will be O of n by the recursive depth. But in this case, the tree is not skewed. The tree is not skewed. It is actually a binary tree, or I should say a perfect binary tree. This is not skewed. This will always have a height, or I should say the level, like number of levels should be log n. Thus, my space, my recursive space can be O of log n if I go ahead by using a DFS. Okay, now I know that I have to use a DFS, but how? Okay, so what a DFS does? A DFS simply does, okay, it iterates like this. Again, there are multiple ways to iterate on a DFS, but like usually you will see that it iterates like this. But technically, I have to make sure that I'm replacing things on the corresponding odd levels. So one thing, okay, obviously in a DFS I have to iterate on things, but one thing I need to make sure is I am keeping track of what current level I am at. Okay, now let's see if I know, okay, I am at this specific level. So technically I have to replace both of these nodes. Okay, makes sense. But then also the same point, making sure that as I am moving down, or as I'm moving down towards my children, that this node should be replaced by this node. 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 Do you see a pattern here? That for a specific node, I'm replacing left and its corresponding right. Or when I say replacing, I mean, okay, I'm just swapping. Now, even if I had the task, again, even if I had the task to replace, let's say, level 2, I would have taken this node and replaced it with, swapped it with this node. Which means that this node's left, I'm swapping it with this node's right. This node's right, I'm swapping it with this node's left. Okay, did it give you some hint? Yes, it should. Now, the same way, for this node's left, it is swapping with this node's right. This node's, again, same way as you can see, this node's left, swapping it with this node's right. This node's left, swapping it with this node's, this node's right, so swapping it with this node's left. So, with this, I could feel like that obviously I have to make sure that I am on two nodes parallelly at the same time. And I would also be knowing which two nodes to swap. So first thing I realized, I want to keep track of a level. I want to be at two nodes at the same time. What these two nodes can be? Obviously, it can be a left node and the right node. Okay, which means that I will start off my DFS, and in the very beginning itself, I might say, okay, bro, I can give you two things. Either I can give you, okay, what is the corresponding current level, and also what is the corresponding left node and right node. Now you might say, Aryan, considering you are at level 1, Here is level 0. Level 0 node is 2, but you are saying that the left node and right node you will keep, which means that 5 and 3 you will keep. And also at the same time, you will also make sure that you are at a starting level, as in like the beginning level. But isn't it a bit confusing that why at the first place I'm starting off not with level 1, because node 3 and node 4, node 5 and node 3 are actually from level 1 itself. I should say this is node 3. I should bring it more here on the left side because this is the input. So isn't it that, okay, obviously I want two nodes to traverse from. Firstly, I will want level, and I would want two nodes, 3 and 5. Even if I forgot the level for now, ultimately, let's see what the maksat is. Maksat simply here is that I'm simply at a specific node. I should swap two nodes. Now, these two nodes need to be corresponding children, which I need to swap. And I'm already passing children's. So let's swap it. Okay, let's swap it. When I swap it, it will simply become 5 and 3. Now, as I'm doing a DFS for this specific child nodes, I again forget about level right now. We'll come on to it later on, but I will go on to its children. So 3 is a child, and I knew that if I had to swap, I had to make sure that 3's left should be swapped with 5's right. So I will simply say that 3's left, 3's left is 8. It should swap with 5 right, which is 34, and I will give the current level. And also, I cannot forget about 3's right. 3's right is 13, and 5's left is 21. They should be swapped. Okay, then these two will do their own DFS. Okay, let's do, and again make sure that their corresponding level can be anything. Now when they will do, again right now I know that these will not be swapped, but okay, let's simply move on forward. Now as they will come down, what will happen? I will do obviously the DFS from all these nodes, which means earlier I did DFS for 3 5, as in like I put the children of both 3 and 5. I took consideration because this is left node, this is right node. So my left nodes left is being replaced with right nodes right. Left nodes right is being replaced with right nodes left. When this actually does the again DFS, this will not be swapped, but still it will call the DFS for his children. So 8, he will say, okay, I'm left node, and he will say I'm the right node. Again the same thing. Left nodes left, 8's left, 8 left is 1. 34's right, 34's right is 8. Just simply swap them. And again, the same thing, that left node's right, 8's right, which is 2. Swap it with 34's left, which is 7. Okay, and then again repeat it. Okay, this is done. This is, sorry, if I just put this is done. Come back to this DFS. For this, 13's left, 13's left, which is 3. Replace with 21's right. 21's right is 6. Okay. And then again DFS, 13's right is 4. Replace it with 21's left, which is 5. And again, at this point, you can simply do the replace, as in like the swap. You simply have to swap. These are the nodes which I'm passing. Simply swap. That's it. Swap the values. That's it. Period. Right? And that's it. That's it. Ultimately, you might say, Aryan, what about this level? This level itself, you can put up anything. Again, for simplicity, you can put up even 0 also. As in when I say 0, which means you can start off with, when I say start off, obviously, and in the very beginning, you have to pass two nodes. Obviously, for the root node, you will pass its corresponding left node and right node, right? And then you have to pass some level. Now, again, now I am saying for simplicity, you can pass either 0 or 1. It doesn't matter at all, because I told you that it entirely matters on how and what you're traversing. Obviously, if you start off from 0, you know that if the level is 0, or I should say level mod 2 is actually 0, which means if it is the even marking you have, then you have to do the swaps of values. If it's if let's say you supposed to start off from 1 by saying okay, the level is 1, then you can simply change the code to say level mod 2, if it is equals to 1, simply do the swaps. Thus, I told you that this should not be a confusing point. You can start off with any value whatsoever. Depending upon if you start from 0, this will change to this value, like this will change to the code here that it should be swapping at even. If you start off from 1, it will change to this, and it entirely is because of that you were taking some children and these children should be swapped right now. That's it. Cool. And again, that's the corresponding dry run and code. So the code simply looks like that. I will start off and call my DFS. I know I have to pass two values. I should say two nodes. I'll pass in the root left and root right. Here, I simply pass 0, but I told you again that this doesn't matter. Although by default, you start off from level 0. This is indicating that, okay, left and right child for a specific root node at level 0, but it looks more good in terms of, speaking. But if you're confused, you can replace it with level 1 and then you can change this line. That's it. Cool. Coming on back, then we have a simple use case that we will start our traversal. If I have reached my leaf nodes, there's nothing I can do and there's nothing I should do. I can simply return. Again, this piece of code I can put up here also as what I did in BFS, if you remember, like this. That's also perfectly fine. Okay, then I will check if the current level is mod 2, which is 0, which means I am at the even level parent. Again, I told you what the configuration means here, because this left and right child of the odd level have an even level parent which I have configured. So I will simply swap their values. Again, the values are being swapped, that's it. And then I will simply call for the left child, its left, so should be swapped with, or I should say should be traversed as a right child with right child's right. And also left child's right should be swapped with right child's left, and simply call the DFS again. And for all the even levels, technically even level parents having odd level children's, will this swap happen? And ultimately we'll get the answer. Ultimately return the root. Because you're traversing on all the nodes, time is O of n, but considering you are only using the recursive depth, which will give you O of log n space, because it's a perfect binary tree. Cool, bye bye, take care. I hope you guys got it. Again, why this question is a bit tricky in terms of DFS is just because of understanding and how we reach to a solution, and why this makes this problem easy is because it's swapping of values rather than the nodes. If the node swapping would have been there, this problem would have been very good. Bye bye, take care. And I do make sure to like if you like it the video. Bye bye.